computing. Okay, so according first, thank you. Okay, nice. So the algorithm is named after Love Grover, who designed it in 1996. He was an Indian-American scientist, and he developed this algorithm for solving the problem of searching. So what's the problem that we want to solve? Say that we have an unordered list which is indexed by some numbers. So like 1 to L tilde. We will see the reason why I'm using the tilde in a minute. Now, okay, I didn't tell you that when you want to ask questions, you are free to open your microphone and just ask questions directly. If you can like interact a bit, I would be happy. But I mean, just at least let me know that everything is going well at some point, just to know that I'm still talking with someone. Okay, nice. So we have this unordered list, and we assume that some of the items of the list are marked as solutions. So there is someone else who have decided that a subset which we call big S of the unordered list is the set of solutions. How many items there will be in the set of solutions, we will call this number M. Okay, which is supposed to be larger than 1. So basically, we have a set somewhere. If we want to find the items which are marked as solutions from the set. Now, as we often do in quantum computation, it's easier to work with things which are power of 2. So we will just define an n, which is the ceiling of the log 2 of L tilde. And at that point, we will just redefine a new set, which has length 2 to the n, which means that we are using a slightly larger set, but we can always fill it with zeros if needed. So say the set in which we are going to look is something like this. 0, 0. And in this way, we will have L elements in the set. Now, first, let's consider the search problem in the classical regime. So how does a classical search perform? Now, say that we have this situation, so that's a completely unordered list. Let's first consider the best case scenario. So if you are very lucky and say that we have only one solution, so M equal to 1, how many iterations, how many times do we need to extract a value from the set? Any ideas about this? You can answer directly, write in the chat. Okay, someone wrote order of big O of L. Actually, yeah, I mean, this is the worst case or the average case scenario. In the best case scenario, we actually have just one extraction, which tells us that the best case scenario is probably not a very good way of evaluating the performances of our algorithm. But if we consider the average case or the worst case, which are actually a little bit more useful, again with M equal to 1, we will need basically on average L half or L extractions, which means that the scaling is always linear. So big O of L. I hope you are familiar with the big O and small little o notation. And yeah, so this basically means that the number of times we need to extract a value in order to check scales linearly with the amount of items in the set. Nice. Okay, so let's set up. Okay, what we will find is that Grover's algorithm allows a different scaling. So it allows an order of square root of L extractions. Now, this is therefore a quadratic advantage. Okay, it's not a huge advantage, it's not an exponential one. For example, if you consider Shor's factorization algorithm, you will see that there you have an exponential advantage, which is like something which goes from an intractable problem to a tractable problem. In this case, the advantage is more modest, and this has led in the past to many people saying, okay, this is not like an extremely good algorithm and so on. But still, I feel that this is a very good example of how people think about quantum algorithms. So let's set up some ingredients for our algorithm first. So I'm just going to quickly review some of the things we are going to use, and feel free to stop me at any point if I'm using concepts or ideas that you're not familiar with. So first of all, okay, we will use quantum states, so objects represented as cats. Searching means drawing a value from a set and compare it. Yes, this is correct. And yeah, so it means that you can think of it as I extract a value from the set, I give it to someone who is able to check if the value is a solution or not. And yeah, this is exactly the role which will be played by the oracle in a minute. Okay, nice. So we are going to use quantum states, and we are going to need to be able to describe measurements on quantum states. For what we need, a measurement is represented by a Hermitian operator, O. So, no, okay, maybe let's not use O, let's use X. And the fact that it's Hermitian, it means that it's equal to its dagger. Since it's Hermitian, we can always decompose it on its eigenvalues and eigenvectors. So it will have this form here. Okay, yeah. So see in the chat the rules for the questions. And okay, so say that I want at this point to check what's the probability of getting an outcome X, given that I have a state psi at the beginning. What I do, as you probably already know, is something like this. So the square, the square modulo square of the projection of psi over X on X. Okay, so this is the first ingredient. Second ingredient, we will need unitary operators. Operators. Okay. So a unitary operator is a operator U, which has the property that U dagger equal to U dagger U is the identity. So what the unitary operator in a sense represents is a reversible evolution. Okay, we will see that this is rather crucial in a second. So every time I have an evolution which is represented by U, I can always reverse that evolution with U dagger. Third ingredient, it's what's called an oracle. I'm not sure if you've already seen this in any part of the summer school. Now, the idea is I want to apply a function. Okay, so a function is an object, a classical function usually is an object which maps an input to an output, which we call f of x. Now, in general, functions are not reversible. That is, it's not always true that given the outcome, I can always go back to the input. For example, an example of non-reversible function is the AND function. You know that if I start with, like, let's write quickly the truth table of the AND function. Oh, sorry. 1, 1, 1. So as you can see, different inputs are associated to the same output, 0, which means that once I get 0, I cannot always get back. Once I get an outcome, I cannot always get back to the input, to the corresponding input. Now, this is tricky to do on a quantum computer because everything we want to do, except for the measurement at the end, needs to be reversible or unitary. This means that we have to find a way to reversibly implement a function. The way is what's called usually the oracle. So we define a unitary operator f, which acts on a larger space. So it acts on an input space tensorized with like an output register. Okay? And this is defined in such a way that the output is again the input register, tensor y f of x. This is, for example, for the AND operator, or any binary operator. Every time I draw this symbol, it means sum base modulus 2. And this symbol you are maybe familiar with is the symbol of tensor product. Tensor product means that I have, for example, a state like x tensor y lives in a Hilbert space, which is created by like the combination, in a sense, of two Hilbert spaces. So it's like a bipartite state. I'm not going to go in more detail about the structure of the process of the tensor product and so on, because it's not extremely needed for what we are going to do now. Let's say that it's just a way to represent things that happen among different Hilbert spaces. Well, okay, let's get started at this point with Grover's algorithm. So the first thing we need to set up is the oracle. So remember that our task is to design a way to find a solution in a set of candidate solutions, in a sense. So how do we understand, how do we see that an item is a solution? It is a solution, so it means that we have to check this function. So say that x belongs to our space. Let's give the space a name. It's probably easier this way. Let's call it E, for example, the space of elements. So say that x belongs to E. Now we define a function g of x, which gives 0 if x doesn't belong to the set of solutions, and 1 if x belongs to the set of solutions. So evaluating the function g on a candidate solution is equivalent to verifying whether the solution is or not, whether the candidate solution is or not an actual solution. Now, again, this function is obviously non-reversible if the set E is larger than 2. And this, okay, because it will obviously map all the solutions to the same output and all the non-solutions to the same output. So we need to make it reversible, and we do it as specified above. So we just define an oracle, UG, which acts on the tensor product of x and y, and gives out the input register as it is, tensor, this. Okay. Nice. Okay. Any questions up to this point? Is everything clear? I hope so. Anastasia, go ahead.
Yes, I wanted to ask, should it be g of x or not, or f of x? I just skipped.
Say it again, sorry. Sorry. Yeah, you're right. I got the wrong letter. Yeah, that's correct. Thank you. Any other questions? No? Okay, so let's go on. So we want to start our search. Okay, so first of all, we have to define an initial distribution to draw from. So let's set up an initial distribution. even before this, I wanted to underline that the oracle is considered to be given at the beginning, okay? So we will not deal with how to design an oracle. It's in general not an easy thing to do. So the specific form of this operator here is rather tricky. And usually when you think about Grover's algorithm, we always assume that the oracle has been given to us, okay? So we are not going to discuss like how heavy it is to do the oracle or something like that. The idea is that this is a black box. So someone gave you the oracle and you're just going to use it, okay? The use of the oracle, like the internal mechanics of the oracle is of no relevance for us at the moment. Also, in the second part of this lecture, when we are going to do a little Qiskit tutorial, I will already give you the oracle as it is, and we are going just to use it. We are not going to discuss its internal mechanism because it's beyond the scope of Grover's algorithm. So we want to use this to start searching in our set. So at the beginning, what we do is to create a uniform superposition of all candidate solutions. So every candidate solution will be represented by a binary string of length n. So let's say that we have, how do we call it? Let's say that we have an element E of the set E. E will be represented by a binary string, something like this, of length n. Okay. Now, what we will do is first to create the superposition. Now, the way to create a uniform superposition of many different solutions is a common trick in quantum computing. So we start from a ket, a state, which is like this, of length n, and we apply on it a Hadamard transformation tensorized n times. Okay, so what's the Hadamard transformation? You have probably already seen this, but just to quickly review, that's this. I hope I got the minus right, but it should be like this. So what it does is basically that it creates, as I was saying, a uniform superposition. To see this, let's just consider what the Hadamard transformation does on a single qubit. So Hadamard applied to 0. What it does is that it gives the so-called plus state, which is something like this, 0 plus 1 over square root of 2. Okay, if we apply a Hadamard transformation tensorized n times, it means that we apply it to every single qubit, and it turns out that what we get is exactly a uniform superposition of all the possible solutions. This is what has been called in the past the idea of quantum parallelism, in some sense. This idea is not parallelism, sorry. This idea has been strongly criticized in the last few years, but the idea is that somehow the power of the quantum computer, at least according to someone, comes from the fact that it can check at the same time many different possibilities, while on a classical computer, you can only check one thing at a time. As I was saying, this idea is not very popular in the current research environment, but it still kind of goes in this direction. So we start by looking at the same time at all the possible solutions. Okay, now, one of the nicest things about Grover's algorithm is that we can think of it in a very nice geometrical picture. So first of all, let's do this. So this is our initial state. Okay, and we know that at this point, this is a superposition, a uniform superposition of all the possible candidate solutions in the set E. Now, what we can do, this is a crucial step, so please stop me if this is not clear. is that we can decompose our object like this. Okay, plus sum over for x, which belongs to S orthogonal, alpha of x. So basically what we do is that we decompose the initial state, so the uniform superposition of all the items, in two parts. This part is the solution part. This part is the non-solution part. Nice. Okay, this means that all the entire dynamics will take place in a sort of a bidimensional space. Now, it's clear that the dimensionality of this object here and of this object here is much larger than just one. Like, they are relatively large space, but we can think of them as I was saying, as a bidimensional space, which means that all the solutions will undergo the same dynamics, and all the non-solutions will undergo the same dynamics. It's going to become clear when we start actually do some calculations. Now, okay, this we can, oh, sorry, this is wrong. It should have been X. Okay. Now, we are going to move directly to this bidimensional picture. So this can be redefined as this object here, plus cos theta naught S orthogonal. Okay, so here now we have to, okay, we define some quantities, the alpha of x, the sin theta naught, and so on. We need to define what they mean in the physical picture. The sine of theta naught is the square root of m over L, and the cosine of theta naught is what is needed for normalization. So it's L minus m over L square root, if I'm not wrong. Okay, nice. So that's the state we have at the beginning. And as you can see, in this way, it's much easier to represent what's going on because it's just a two-dimensional space. Once again, the fact that we can think of the dynamics in the two-dimensional space means that in practice, all the solutions will undergo exactly the same evolution, and all the non-solutions will undergo exactly the same evolution. Everything clear up to this point? Okay, there is a thing which comes to my mind right now, which is that I didn't define this object. So the space solution orthogonal is obviously the space of all the things which are not in the solution set. Okay, once we map them to qubits, they are like the orthogonal space to the space of solutions. Okay, nice. So for easiness of representation, we can define the projector on the solution space which we call pi s, and this is the sum over all the solution space. So let's write like this, big S x x. And since the solution space and the non-solution space create the entire space overall, the projector on the non-solution space is the identity minus the projector on the solution space. Now, okay, say that at this point we have mapped our set of candidate solutions to this quantum computer, and now we have done a lot of effort and we decide to just waste all of it, and we just do random sampling out of it. So we just extract something from the random computer. You know that if you do a measurement, you are somehow randomly sampling the set of all the possible outcomes. So, okay, what's the probability of finding an element of S upon measurement? Any clues? Any ideas? So I have this state here, or this state here, if you prefer. What's the probability of finding an object which belongs to S? Any clues? M over L. Yes, this is true. So let's just see this quickly. Cos squared, I guess in this representation is more like sine square. Sine squared theta naught. Yeah, exactly. Sine squared theta naught. So basically M over L, exactly. So let's see this quickly. So let's define this probability A. And this probability is given by, okay, the initial state psi naught, which I've not defined. Okay, is this. Okay, psi naught. And then I just project on the solution space. Okay, this is the same, as you can see, as doing the norm, like the projection of psi naught on S squared, which, as you can see, is sine square theta naught, or M over L. Okay, this is not surprising, because if the probability, okay, think of M equal to 1 for the sake of simplicity, if the probability scales, so the probability of finding a solution scales as 1 over L, if we assume M equal to 1, which is exactly the classical scaling. This is not surprising. So why is it the classical scaling? Because if the probability is 1 over L, it means that I have on average to look for to extract L values in order to get the solution. This is not surprising. It's exactly what we had in the classical case. Okay, so we completely recover the performances of the classical case. So far, we have not used our quantum advantage in any way. So that's not surprising. We will see that by doing some unitary manipulation of our states, we will get to a situation in which instead this scales as 1 over square root of L. So we'll get our classical, our quantum advantage. Okay, let me check that I've said everything needed. Yes. So now we have to engineer these unitary operators in order to turn our linear scaling, our boring classical linear scaling, into an interesting quantum scale, into an interesting quantum advantage. So the idea in which we think about it is the one of an so-called iterator. What is an iterator? An iterator is like a unitary operator that we apply a given number of times. We will have to think about how many times. Now, the nice thing about thinking of it in a bidimensional space is that at this point, we can represent our states on a Cartesian plane like this. Okay, so on the x-axis, we will put the S orthogonal, and on the y-axis, we will put the S. So keep in mind, again, that these sets are not simple, like they are huge spaces, potentially. Actually, if you want to look for to have a proper quantum advantage, you usually are considering a huge set of candidate solutions. But due to our mapping to a bidimensional space, we can represent it like this. Okay, so our state psi naught, which again in this bidimensional space was something like, let me check again. Okay, sine theta naught solutions plus cosine of theta naught not solutions, at this point can be represented by a vector in the space, and it will be something like this, psi naught. Okay, now this is, sorry. Okay, so this is our psi naught vector. Okay, now we want to design some kind of unitaries that have two properties. So required properties. First of all, we want it to remain in this bidimensional space. This is an important idea, okay? Because we want to, so the idea is that everything which happens to a solution has to happen to all the solutions. Everything that happens to a non-solution has to happen to all the non-solutions, okay? We don't want this bidimensional picture to break, like if something happens to a solution, but not to another solution, we cannot anymore work in this representation. The second thing that we want to do is that, as we saw earlier, the probability of getting a solution is basically represented by this length here, that at this point is sine of theta naught, if this is theta naught, right? So what we want to do is somehow to rotate this vector in order to increase the projection on the S axis. So we want to increase the S projection of the state. Nice. So let's get started. First of all, we will need to use our oracle, okay? So we assumed at the beginning that we are given an operator UG, which we don't care how it's designed. Okay, so let's introduce a slightly quicker notation. When I have a tensor product like this, I will write something like x comma y, just quicker. Okay, and this is x, y, sum modulus 2, again f, g of x. In practice, what happens? Okay, in practice, if I apply this UG to an x and I give as the output register, I start with a 0, I get the same thing if x belongs to the set of known solutions and a flipped qubit on the other side if x belongs to the set of solutions. Obviously, if I apply this to the set of ones, what I get is x1 if x is not a solution, x0 if x is a solution. Okay? Now, okay, this is interesting, but that's not exactly what we want. So this is the usual way of defining an oracle, but we want to use something a little bit nicer for us. So let's think of applying the oracle on the minus state. What is the minus state? The minus state is 0 minus 1 over square root of 2. So it's a superposition of 0 and 1, which has some nice properties like this. So think of applying the oracle to this object here. Now, clearly, what happens is that everything is linear, so I can rewrite it like this. So it's UG applied to x0 minus UG applied to x1, okay, with the normalization factor at the beginning. Okay, what I get at this point, just by applying what I've written above, let's assume at this point that x belongs to S1, so it's not a solution. What I get is 1 over square root of 2, and everything remains the same, basically. Right? Yeah, minus UG x1. So I get exactly x minus. So it's left unchanged. But if x belongs to the set of the solutions, what happens is this. Okay, I have exactly the same thing. Nice. And then what I have is, at this point, since it is in the set of the solutions, the output register will be flipped on both sides. So I will get x1 minus x0. Okay. As you can see, this object here, where is the, okay. This object here is exactly the same basically as the input object here, but with a flipped sign, with a switch sign. Yeah. Okay. So what we got is a minus x minus. Now, sometimes in the literature, this idea of an oracle which marks a solution by adding a minus is called a phase oracle. Okay, so the idea is that it's something that marks a solution by adding a phase, the minus, for example. Okay. Okay, so basically what happens when we apply our UG to the initial state. What happens is that every solution in the initial state will be marked by a minus sign. Okay. Okay. So now think about. Okay, we have defined the action of U on specific states, on specific eigenstates in particular. So let's define its action on this object here. So where gamma is some superposition, okay? In particular, for example, the psi naught, if it's the first step. So we can always decompose gamma in the solution space and the non-solution space. How do we do this? We just project. So psi s orthogonal gamma tensor minus at this point. Okay, let's do it more slowly. Plus pi over x. Okay, 1 second. Pi over s gamma tensor minus. And at the front, we still have the UG to be applied. Okay, so what happens when we apply this? Now, this object here, we don't know what gamma is, but this object here always belongs to the S orthogonal subspace. While this object here, again, we don't know what gamma is specifically, but always belongs to the S subspace, which means that what we get is that the S orthogonal subspace will be left unchanged, so gamma tensor minus, but a minus will appear here, gamma tensor. Okay, sorry, we should keep the projectors here. Gamma tensor minus. Okay, I want to stress that this minus is really probably the key of Grover's algorithm. So it's what allows to determine whether a candidate value is a solution or not. Okay. Okay, so let's just, let's now try to represent what it means geometrically. So we want to understand its geometrical meaning. To do so, remember that pi of s orthogonal is the identity minus pi of s. And so what we get in the end is this. So we have identity minus pi of s, gamma tensor minus pi of s, gamma tensor minus, which is the identity minus 2 pi of s, gamma tensor minus. Anyone can see what's the geometrical meaning of this thing? So if I start from gamma tensor minus, ignore the minus, okay? At this point, since the minus is always left unchanged, we can completely ignore its existence. So what happens is basically that we start with the gamma state, and we are mapped by UG to a state which is the identity minus 2 pi of s, gamma. Now, that's a reflection along some axis. Yes, which axis? This is true. That's all a game of reflections. Any ideas of like what kind of reflection this is? Okay, let's go back 1 second. Okay, let's go back 1 second. The solution parts gets reflected exactly. So if we go back to our initial plot, let's change color. We get that, for example, if gamma is our initial state, should try to do reasonably. When we apply our UG, the effect is 1 minus pi, 2 pi of s applied to psi naught, and that's in practice a reflection on the S orthogonal axis. So this angle here is obviously the same, theta naught. Okay? Okay, this is already quite nice because we have done something which depends on the fact that something is a solution or not a solution, but it's not what we, honestly, it's not enough. Remember that our target is to do something like this. So we want to increase the S projection of the state. And so far, we have not changed the S reflection of the state. So, okay, but not wonderful yet. Once again, I'm going to completely ignore the ancillary minus state. The reason is that it's left unchanged. So I can always assume that it comes in at some point. I just measure it at the end, but since I already basically know the result, I can always measure it in the plus minus basis, for example, and it will not in any way affect the other state. So we can just ignore the existence of this ancillary qubit, and we will see that in the Qiskit implementation, it's not even there. Okay, it's just a way to convert our original oracle, which has this form here, into a different oracle, which has the form of adding the minus. Okay. This is not enough. The second step of the iterator is the reflection around psi naught. Okay, so let's define an operator R psi naught, which is again a unitary, which has this form here. At this point, you probably realize that the form identity minus 2 state or 2 times a state minus identity is a reflection. Okay, so this is a reflection around psi naught. So this means that if we start from our green state at this point and we reflect it around psi naught, which remember is this, we are going to do like, I'm horrible at this thing, I guess this one. So, okay. So we are going to move in this direction by 2 theta naught. Remember that basically, okay, we were at theta naught, then we move down with the oracle, and then we reflect around psi naught. So it's actually a 2 theta naught reflection. Okay, this is interesting because at this point, you see that we have increased our projection by a bit, right? So we are going in the right direction. What I'm going to do now is to try to prove that this thing actually works. Okay, I think it's interesting to see that this is not like some black magic, how it could possibly look, but we can actually prove properties of this object. Okay, okay, so bear with me if the proof could be potentially slightly boring, but I think it's meaningful to show how one proves something like this. So, okay, let's first define a Grover step or a Grover iterator, which at this point is the composition of the oracle reflection plus the reflection around psi naught. So we define G, unitary operator, as R psi naught. R psi naught applied to UG. Okay, let me write here UG tilde just for the sake of preciseness, because actually we are neglecting the minus. So we assume that once inputs the minus, evolves with the oracle, and then traces out the minus. So this is just to remark that UG acts only on the input register, not on the output register. But we know we know how to go back to UG if we want. So let me write down the claim. Okay, any questions up to this point? First of all. No questions? Fine. Okay, so let's move on for this quick, I hope, proof. So the claim is basically that when I do this, so I apply j times on the initial state psi naught, what happens is that I get the cosine of theta j as orthogonal plus the sine of theta j s. Nice. But the interesting thing is that theta j is 2j plus 1, theta naught. Okay. Okay, so basically what we are proving is that this rotation actually happens as we expect. If we put j equal to 0, obviously we find the initial angle, but if we put j equal to 1, we find 2j plus 1, so 3 theta naught, which is actually the angle which we see here. So this is 3 theta naught. So looks correct, right? Now the proof, like just, yeah. Actually, looking at the time, it's probably better to sketch it without going in super detail. And okay, the proof is done by induction. So the idea is that we prove that for j equals 0, this is obvious. I mean, that's where we started from. And then the inductive step means that if this holds true for gj, then it holds true for gj plus 1. Okay, how does this work? Basically by just applying the operator. So I assume to be given the state of this form, cosine of theta j is orthogonal plus sine of theta j s. Okay, no, sorry. Okay, and then okay, I just apply UG, and then can we set theta not as 90 divided by 2j plus 1? What I mean, theta naught is not something we can set. Theta naught is just like the angle where we start from. I mean, since the sine of theta naught is square root of m over L, and we cannot control neither m neither L, neither L, because they are both like starting points of the problem. We cannot set theta naught in a sense. They are given. Okay, it's given from the beginning. Okay. Okay, so okay, so we basically apply. Okay, thanks for the question. And we basically apply all the operators. We use some trigonometry equivalences and so on, and we get to our solution. Yeah, I was thinking of doing the proof entirely, but probably looking at the timing, it's better to not to do it in detail. There are more interesting things to say. Okay, now if it's okay for the organizers and for you all, I would take maybe a 10 minutes break until past. Is this okay for you?
On watching on the schedule, there will be like a 10-minute break on 12:50. So it's like in 30 minutes there will be a break. So right now, I think we can maybe do like a 5-minute break or something. But due to the schedule, the official break will be like in 30 minutes.
Okay, so maybe let's move on until the official break, I would say, if it's okay for everyone. Okay. Sorry, wasn't sure about this. Okay, let's move on. Any questions? Yeah, I mean, I guess no. Like, I didn't prove the theorem, so anyhow, okay. This we have not proven this, but this holds true. Okay, so what we have is that every time we rotate, we get to a new angle, which is given by the 2 theta naught by this equation here. Okay. So now, okay, obviously there is a problem. So every time we move, we basically add 2 theta naught. Okay, so let's redraw it quickly. So we have the non-solution space and the solution space here. And okay, so we have at the beginning our theta naught somewhere. Let's say like this. So naturally the theta naught angle is this. Now I keep rotating. So this is, oops, sorry. This is 2 theta naught. So we are at this point at 3 theta naught from the x-axis. And then we rotate again. So we get somewhere here. This is another 2 theta naught. Obviously, I mean, at some point we will need to stop, because if we rotate too much, what's going to happen is that at some point we will pass this level, and the probability will start decreasing again. So we need to find a way of computing what's the optimal amount of Grover's iteration. So what's the optimal amount of Grover's iterations? Okay, so again, the target is not to rotate too much, because if we rotate too much, at some point we will start having a probability which decreases. Okay, this is probably worth showing. So the claim in this case is that the optimal J is JL, which is pi over 4 theta naught ceiling. Maybe the optimal amount is attained after some number of full revolutions. Interesting. I've never thought about this, honestly. Possibly, but what I would say is that, I mean, oops, sorry, I'm in the wrong place. Okay. I mean, possibly, but at the same time, we still want to keep our advantage. Okay, to get our advantage. If we propose a number of iterations which is extremely large, we will maybe get a very high probability of getting a solution, but at the same time, it's a bit like we are not anymore sure that at this point we will get an advantage, because at this point the number could scale like L potentially. Okay, we will see that in this way it scales like square root of L. So that's why it's advantageous. And also there is another thing, I think, to answer this question, that is maybe, okay, we will not get to 100% probability of getting a solution. So also in the end, we could get something which is not exactly a solution. But at the same time, if we have the oracle, it's very easy to check if something that we get is a solution or not. Okay. This is related, even though it's not the very same thing, to what we have in the case of NP problems. So the problem is somehow hard in a direction, but it's easy to check if something is a solution. I mean, this is not an exponentially difficult problem, but still it's easy to check if something is actually a solution. So like the fact that there is some error at the end is not a huge problem, as we will see. We will anyhow discuss like how big this error is. Okay. Okay, so let's prove this. Okay, for this it's probably better to actually prove everything in this case. So the fact that JL is the ceiling of this thing means that the payment of this thing means that this object pi over 4 theta naught is between these two integer numbers. By the way, Oleksi, was the answer satisfactory? I hope. Okay, I hope so. And okay, so okay, thank you. Notice that this object here, pi over 4 theta naught, depends only on the structure of the problem. Theta naught is determined by the number of solutions and the dimension of the search space. So it's something that can be determined from the beginning, which is important. I mean, if we have to design a machine to search for something, I want to be able to determine how many times I have to run the machine before starting. Okay, so let's multiply everything by 2 theta naught. So we get this pi over 2 theta naught JL plus 2 theta naught. Let's subtract theta naught times 2JL plus 1. Okay, and so what we get is minus theta naught, so equal pi half minus theta naught 2JL plus 1 smaller than theta naught. Okay, now let's subtract pi half and multiply by minus 1. And we get to the final thing. So theta naught plus pi half larger or equal theta naught 2JL plus 1 pi half minus theta naught. Okay, just for, okay, pi half minus theta naught 2JL plus 1 theta naught plus pi half. What does this mean? I mean, this at this point is the angle theta JL, if you remember the expression of the angle, which was here. Okay, so this means that the angle at iteration JL is at this point such that pi half is with a theta naught precision inside it. Yeah. So basically what we are saying is that, just to do it quickly. Sorry, maybe this is very clear. Okay, so it means that like the boundaries are these. So this is pi half, obviously. This is theta naught, and this is theta naught. And what we are saying is that at that iteration, we are somewhere in here. Which means that if we do another iteration, we will certainly lose precision. Okay, so this somehow contains the pi half, which is the ideal, angle. Okay, now importantly, at this point, we have to prove the quantum advantage. Because, okay, how many times do we need to do this? Prove the quantum advantage. So this is crucial because if in the end we have to do as many rotations on average as we would do in the classical case, then we have wasted a lot of time and effort. So let's have a look at this thing. JL, the number of ideal iterations, is pi over 4 theta naught. Okay? Now, theta naught, give me a second. Okay. Nice. Okay. Theta naught, as we remember, was, okay, the sign of theta naught was determined by m over L square root, right? Now, okay, so theta naught is the arc sign of the square root of m over L. So JL, bear with me, I'll do some slightly sloppy calculations, but this is going to be more or less, apart for something which is not relevant for the sake of the scaling. It's like this, which means that if L is sufficiently large, we know that the arc sign approximates to its argument. So if the argument is small enough, so what we get is basically something which scales like this, which at this point scales like square root of L. Okay, this is interesting because at this point, this is an evidence of a quantum advantage. So remember that how many times did we have to interrogate the oracle on average in the classical case L? In this case, we have to interrogate the oracle only square root of L. So it's a quadratic speedup. As I was saying earlier, the quadratic speedup is nice, but it's not wonderful. Like, it's not an exponential speedup. So it doesn't transform like a non-feasible problem into a feasible problem. But it says something quite interesting. Just to add something which doesn't work too well, I would say, I would add the fact that everything here is assumed to be completely fault tolerant. This means that we assume to be able to perform operations and to have qubits that are not affected by any physical error. This does not directly correspond to reality. Okay, this is not something that in reality happens, and this is one of the reasons why this kind of algorithms is an interesting proof of concept, but at the same time, it's, I mean, not particularly easy to implement in a direct application. Okay, now, let's conclude a couple of calculations before the break. Okay, so what's the error with the optimal? With the optimal JL. Okay, so questions about the quantum advantage and so on. Sorry, forgot to ask. No questions? Okay, move on. And okay. So, okay. At the end, okay, so the optimal state after.
I think there's a question from the chat.
Oh, sorry. Isn't JL the number of reflections we need to do and not interrogations of the oracle? It's the same. The thing is that every time we apply the G operator, so if you remember the G operator, where is it? Yes. So the G operator is this one. So a reflection is actually the G operator. And so a rotation by 2 theta naught corresponds to the G operator. As you can see, the G operator includes one interrogation to the oracle. So counting the number of reflections or counting the number of interrogations to the oracle is actually the same thing. Is this okay, Yuri? Okay, very good. So the state after an optimal amount of iterations is given by the Grover iterator to the JL power applied to the initial state, right? Okay, like now the point is, how far is this? How probable is it to get a solution when measuring on GJL psi naught? Question mark. Okay. Now, how probable is this? So how do we compute this? Any ideas? Any ideas on how to do this? Maybe we can use the word, yeah, kind of. We can do it more directly, actually. Yeah, I mean, it's basically the same thing. We could try to like low upper bound the error by using the fact that we are within a theta naught angle of pi half, or we can do it more directly in a sense. So we can just project our state. Yeah, and now nice answer. We could actually upper bound the error, I think, like this. But we can directly do the calculations. I mean, at this point, we know what's the projection of the GJL, G to the JL power psi naught, because we know that at this point we are at an angle which is 2j plus 1 theta naught, right? So, okay, yeah, sin squared of theta JL. Okay, now you are actually using your idea in order to upper bound this error in terms of the initial parameters. So we know that at this point we are inside the red cone in a sense. So the sign is always larger than the sign of, for example, this, than the sign of this angle here. So this is larger than the sine square of pi half plus theta naught. Now, this thing here is, if we use some trigonometric identities, the cosine square of theta naught, which again is 1 minus the sine square of theta naught, which is 1 minus m over L. So yes, we can actually bound the error. We see that if L is large, is much larger than, if L is much larger than m, it means that theta naught is a small angle. And at this point, what we have is that the probability of getting a solution, so let's call this P of solution, is approximately 1. Obviously, the thing is, if we are doing a search in which there are a lot of solutions, the angle theta naught will be larger. In the limit, the angle will be 90 degrees if everything is a solution. At that point, this algorithm doesn't work too well, but at the same time, it doesn't make too much sense to look for solutions if all the elements are solutions themselves. So, okay, summary before the break. How do we implement this thing on a circuit? So how do we do this? Okay, you have probably already seen the quantum circuit usual representation. So the idea is that I start here with a state, which is, this is just 0 represented in n qubits. Okay. Now, okay. And then I need also the ancillary operator. Do you remember the one for the oracle, the minus, which comes in and allows us go from the oracle, which to transform the oracle into a phase oracle. And okay, so first of all, let's prepare this ancillary degree of freedom. So we want to create a minus state from 0. Do you know how to do this? Any ideas? How do we transform minus 0 into a minus using like the gates we know? A Hadamard operator, yes, but it's not enough. The thing is, if I just do this, yeah, so I need a Hadamard operator and the x. The reason is, if I just do a Hadamard operator on 0, what I get is 0 plus 1 over square root of 2. This is not exactly what I want, but if I do first the not operator, then a Hadamard, so an x, which is basically a not, what I get is exactly what I want. So it's 0 minus 1 over square root of 2. Yes. Be careful, the operators don't commute, so I have to apply them in the right order. Okay. If I just apply, for example, the opposite way, first the Hadamard and then the x, you can see that nothing changes. Like the state, the plus state, is invariant under the action of x. So this is the minus state. So first, I apply an X. We may also use ZH, I guess. Yeah. I mean, there are many possible identities. ZH, yes, of course, this is correct, because you can, so ZH means that first we apply H. And so we go from, so, okay, we go to this thing. Yes. And then we apply the Z, so we get 0 minus 1 over square root of 2. Yes, that's correct. Yeah, there are many possible ways of getting there. Thanks, Alexei. So we have this, and then we apply the Hadamard. So at this point here, we have a minus, okay? So this is what we need. Now, okay, we get started with the proper Grover algorithm. Let me just write this like this, which means that the cable, the wire usually represents the qubit. In this case, it represents n qubits. And okay, also here, we need to prepare the initial superposition of all the possible states. So we apply a Hadamard. This time, let me write it like this, which means that it's applied on all the qubits. So just to recall, this is create equal superposition of all states. Nice. Now let's include this thing. Okay, now we have the oracle. Remember that the oracle acts on both, because we need to use the minus in order to transform the oracle into a phase oracle. Okay, after the oracle, we can just ignore the minus state. We know that in any case, whatever happens inside the oracle, we will always get a minus state here. Okay, which means that ignoring it means, if you want, we can, for example, measure it in the plus minus basis. If you like, you will always get the same result. So it's completely useless, but just as a way to ignore it. Sometimes people write it like this, which means just face out, ignore. Okay, after the UG, we need to apply the rotation around the psi naught state. Okay, just to recall, the psi naught is the state that I have here at this point. Okay, now this overall is, give me a second. Overall, this thing here is the Grover iterator. Okay, so which we called G. So we have to apply the Grover iterator JL times. Okay, so this thing has to be repeated JL times. In the end, what we will do, here we will have again the n space, and we will do a measurement on the computational basis. Okay, so at this point, we will get a solution with the probability that we have determined before. Okay, now this is the first part of it. Just to, I'll just quickly summarize what I'm going to do in the next part. So first of all, now we have solved on a quantum computer the problem of looking for a solution or more solutions in a set, in an initial set. Now there is something which you have not considered, which is that we always assumed, I'm not sure this is very fair, but we always assumed M to be known. Okay. What does it mean that M is known? It means that we basically know how many solutions we are looking for, which means that the person who has designed the oracle has told us how many solutions are there in the solution set. This is not an obvious thing, actually. Like, in principle, we could think, yes, we are given an oracle, but no one told us how many solutions there are. So we need to find a way of doing Grover search without having the knowledge of how many solutions we have at the beginning. Clearly, we cannot directly use Grover like this, because the parameter theta naught, which is crucial everywhere, depends on M. It's square root of M over L arcsine. So we need to find a way of solving this issue. We want to be able to find solutions also of problems which we in which we don't know how many m's there are. I think this is also meaningful because the solution of this thing will allow us to introduce some of the algorithms of, so in a sense, the other family of algorithms, so the ones based on the Fourier transform, basically. And so, yeah, in the next part, we'll go through the so-called quantum counting problem. So how many solutions are there in our set? I'm going to go a little bit faster on the part about the Fourier transform because it's a rather intricate circuit to introduce, and I really don't have the time to go into detail about how it works. And we will just assume that someone has designed a way to do a quantum Fourier transform efficiently. And I think that's all for before the break. Is it okay, Anton?
Yeah, it's okay. Like we're just in time, so we have 2 minutes before break. So if anyone can have a question, I temporarily turn on the option of unmuting themselves, so you can ask the questions.
Okay.
Okay, it seems that there is no yeah.
Isn't the Hadamard operator needed at the end of the algorithm? Why? I don't think so. But no, I don't think so. Why, Julia? Like, no, because at the end I have just no. I don't think. Yeah, of course. So the idea about looking at the space as two-dimensional is that everything that we do depends on, so take an initial state of some kind, so one of the solutions or the non-solution. Okay, take one of the solutions. Everything that happens to the solutions depends only on the fact that it is a solution. Okay, so all the solutions will undergo the exact same evolution because the UG will first map, like the reflection due to the oracle will first reflect them around the S orthogonal axis, and then the rotation will create a rotation. But the solutions will evolve all in the same way. Okay, this means that we can just think of them all together. Okay, this is the reason why I put here the first requirement. So remaining in bidimensional space means that everything that happens to the solutions has to happen to all the solutions, and everything that happens to the non-solutions has to happen to all the non-solutions. Okay, this is important as a requirement. If you had something which happens to a solution but not to another one, for example, you would not be able to represent this on a bidimensional space. Is this okay, Yuri? Thank you. Okay, I guess it's break time at this point.
Yeah. So we meet in 10 minutes.
Nice, thank you.